Welcome everyone. I'm Dr. Ibn Raj, a faculty and also the head of Computer Science and Engineering Department here at IIT Kottayam. And in this session, I'm planning to talk a few things about asymptotic analysis, and also I'll be talking a little bit about why do we require this sort of asymptotic analysis, or what is the significance, and also I try to introduce certain aspects which will kind of be interesting if you are very new to this sort of analysis of algorithm. So most of the time, the questions, whether it is from working professionals who are in the industry or from a normal UG student, most of the time they have a feeling that this sort of analysis is something which is totally theoretical and it has got nothing to do with the actual programming style or with the actual programming what you do. Right? So most of the time, I used to pitch this question: how do you actually compare the relative speed of two different algorithms? Because you have a particular problem and you can solve it in different ways. How do you choose the best one out of that? Right? So just imagine that you are going with something like, say, if you are imagining, or if you are taking execution time as one parameter, it is not going to be a good metric, because it is basically specific to a particular machine, and also it all depends on where you are executing your particular program, right? Or if you are taking the second metric, say, imagine that you are going for the number of statements which is being executed in that particular program. That is also not a good measure, because the number of statements executed varies from one programming language to the other one, and also it depends on the style of the individual programmer. So the ideal solution is to express the running time in terms of an algorithm as a function of input size. So we assume that even if you have a very large input, still how does the algorithm is going to perform? So you're actually kind of giving us kind of stress test to this algorithm, so that how long or how it is going to surpass or how it is going to perform if it is having a very huge number to kind of deal with. Right? So we'll take a look at this sort of asymptotic analysis. So let me just show you the whiteboard. So just a second. So just give me a second. Right. So as I mentioned, it is ideal to measure the order of growth of a particular algorithm, which doesn't depend on the machine hardware or the programming style or the programming language which you are using. And the biggest significance is that you don't have to implement the algorithm. You can just analyze your particular algorithm just with the pseudocode, or even with the algorithm as such. So imagine that you are planning to build an algorithm which is having millions of lines of code, right? So without even implementing that, you'll be able to predict, or you'll be able to tell whether this is going to be a better algorithm than the other algorithm or not, right? So that is all about asymptotic analysis. So for example, if I'm showing you this particular pseudocode, so you are asked to find the sum of n natural numbers. You can do it in different ways, right? So if somebody's going with this kind of a function, so let's assume he's just making use of a normal return statement, just applying the direct formula of n multiplied with n plus 1 by 2. So if you are considering this as a function of time, definitely whatever is the value of n, it is going to definitely take a constant time. So it is going to remain constant irrespective of whether you have a value of 1,000 or 10, or whether you have 1 million or 10 billion or n billion, right? And if you move on to the other function, fun2, so here you have, if you're converting this in terms of mathematical expression, you will be getting something of this sort. You have C2n plus C3. So how this has happened is, you're assuming that the statements that is executed, this and this, that is going to always take constant amount of time. But if you are taking this particular portion, this is going to run for n times. So that cost, I'm assuming that if I'm assuming that this is going to take a C2 cost and this is going to take C3. So C2 will get executed n times. So C2 multiplied with n, and in addition to that, you will have C3 on top of that. So you will have this kind of an expression, right? So mathematically now we are able to compare these two algorithms without even implementing that particular algorithm in any of the programming language. So the third one, if you are taking, that's a little more complicated. You have two loops here, and again, if you are again writing that, you will get an equation of this sort. So you have three different functions. Now these functions can be easily compared without much effort, right? So why do we still want to do this? So again, so imagine that you want to compare the execution, or compare the compare the efficiency of two different problems. It should be on the same constraints. So if you are comparing a fish and a monkey, and if you're asking the monkey to swim in water, it's not a fair deal, right? So here what we're going to do is we assume that everything is a uniform thing, and you are kind of converting these programs into a mathematical function so that you can compare these functions, and that will ultimately tell you which is the efficient function, right? So in a nutshell, this is what all about is this asymptotic analysis, right? Now, again, if you think about this asymptotic analysis, there is one more thing which is kind of very relevant to this. So let me just take that up. So just a second. So if you think about a program like this, right? So here also we are trying to find out the sum of n natural numbers, the same code. But what I've done is, if it is like n can be any value, so in such a case you will have like all these things, and mathematically you can write it in this way. Imagine that I'm changing that particular line of code in this way, such that if n is going to be even, then it will not execute anything. It will just return 0, just as you can see here. And if it is a odd number, that is, if the value of n is odd, then it is going to get executed for n times, right? So here you have a condition. So I can say that in the best case scenario, it is going to get it done in constant time. So whenever the n values even, I don't have much work. It will just execute one line of statement and it will come out of that, right? So here in these cases, I can say that in the best case scenario, it is going to run in constant amount of time, right? And in the worst case, it is going to get it done in sort of n times, right? Or of the order of n. So the growth is in the order of n, right? Now how about average case? So in the average case, we assume that half of the time let it be odd, and half of the time let it be even. So if that is the case, then what happens is at the maximum I'll have n by 2, and still I can write it in terms of n by 2 multiplied with c1. So these three cases come. So whenever we talk about any programming language, or whenever you're developing a software, everybody is interested with the worst case scenario. So if you're building a program and you're saying that, hey, my program runs best, or it gives me the output, if I have this kind of set of input, it is going to give me it in maybe 1 nanosecond, right? But if you're not mentioning about what is the worst case scenario, nobody is going to buy your software, because everybody wants to know how this program or this software is going to perform if you have a kind of worst case input, right? So that is the significance of worst case, average case, and best case. Now, so how do you actually say this in one sentence? Whenever somebody is asking you what is the performance of your algorithm, it's really difficult to tell that, hey, in the worst case this is this, in the average case this is what happens, and in the best case this is what happens. Now, how do you say it in terms of one statement, right? So for that only we have something called 3 different asymptotic notations. So these 3 asymptotic notations, what it does is, it says that you have something called a big O. So what big O says is that in the it says that whatever that happens, at the maximum, this is going to take only this much time, or this or equal to this time. So let me just give you an example. So let's assume that you have a particular problem. The problem is traveling from, let's say, Trivandrum to New Delhi. So this is your problem. So I can solve this particular problem or this particular issue using different modes of transport, right? So let me assume that if this is my problem, I have a different solution. My first solution could be maybe I can go by train, and my second solution could be by flight, right? And let me my third option could be, let's assume I'm going by walk. So the same problem, but I have three different solutions over here. Now I'm also just writing the approximate time taken by these particular this particular solutions. By train, let's assume that it is going to take 48 hours, and by flight, it's going to take, say, at the maximum 3.5 hours. And by walk, if you're going, I'm just writing here, it's going to take 90 days. Right now, so I have the same problem. Out of this, I want to know which one is going to be more efficient. So here, straight away, you know that the answer is it's by going by flight, right? But if somebody is asking what is the maximum time it's gonna take to solve this particular problem, I can say that, hey, it's going to take at the maximum 90 days. Even if you go for any of the solution, at the maximum, it is going to take only 90 days. But it doesn't make any real sense. But just to make you understand this concept of big O, I was just mentioning this. So for example, I can say that even if somebody is asking, imagine that I don't know how much time it is going to take by train, right? So I can write that by train, if you go, definitely by walk, it is going to be 90 days. So definitely it is not going to be take more than 90 days. At the maximum, within 90 days, you are going to reach Delhi, right? So the point which I'm trying to say here is, so if you know certain things, which is already like, this is the bound, or this is how much resources this particular solution is going to take, then easily you'll be able to compare these two things and write it in terms of three different things. As I mentioned, the first one is big O. The second one is theta, and the third one is omega. So what it does is, the big O, it kind of gives you the upper bound. So if I'm saying for traveling from Trivandrum to Delhi by train, it is not definitely going to take more than 90 days. So that I can write it in terms of this big O notation. Now, if I'm saying, but still just assume that I don't know by how much time it's going to take by flight, right? But at this time, I assume that I know how much time it's going to take by train. So in those cases also, I can express it in terms of a big O. At the maximum, it is not going to definitely not going to take beyond this particular time, right? So using these notations, easily we can make use of analysis of algorithms. And the most important thing over here is, you don't have to implement any of these algorithms. Without even doing that, using these notations, you can easily come up with a solution, or with a comparison of different algorithms, and decide, hey, which one is going to be the best algorithm. So this is a very brief and small introduction about asymptotic analysis of algorithms. So thank you very much for listening.